Okay, here we go. We're going to record this for you. Hopefully people watch this and it helps them. We have a quiz tomorrow. Exponential. First one, we have tell whether it's exponential growth or decay. So if you look at the base of the exponent, and that number is going to be between 0 and 1, then it's going to be decay. So the first one's decay, this second one's growth, and this next one here is also growth. Alright, so that one's going to be a decay. This one is a growth. And just a little follow-up here. What percentage would this one here be growing by? 104. No, not 104. 4. 0. It's growing at 4%, right? If it was 104, it would be a little bigger than 1.04. It would be 2.04. Well, 0.4 is the decimal part, right? And so that means if it's more than 1, it's growing. And so the part after the 1 is the percentage part. So this is really growing at 4% growth, right? Yeah, 0.04 is the decimal. So the 1 would be, yeah, it's growing. It's more than 1, right? If you're multiplying by something that's more than 1, it's getting bigger. If you're multiplying by something that's between 0 and 1, it's getting smaller. That's why the first one is decay. Okay, what is this one decaying by? 10%. So it's decaying 10% each time, which means you're taking the amount and multiplying it by 90% because you're getting 90% each time. You know what I mean? So just a little added bonus information there. This one here, hold on. This one here is 5, so it's really actually 400%. But that gets a little crazy. So the growth factor here is 5. That one's growth. All right. Everybody's got to go. All right, so number 4, we have a negative 6 starting amount, and it is 1/2 to the x, so this is going to be a decay. And so we just fill out this table of values. Let's get a feel for what's happening. So let's start with to the 0 power. 1/2 to the 0 power would be 1, and 1 times negative 6 is negative 6. So I'm going to get a negative 6 in there. If I take 1/2 to the first power, I get a half. And so negative 6 times a half is a negative 3. So the numbers are getting smaller or bigger? Well, this one's a little weird. Okay, they're getting smaller, but smaller bigger is actually bigger. Oh my gosh, this is confusing. So anyway, when you graph this one, it's going to be a decay, but it's an upside down decay. So it's going to be going, if I just, well, I guess we'll have to sketch it eventually, but this one kind of goes by weird values. But let's just say I'm down here at, I know they're going to get really negative. Okay, so negative 6 is somewhere in here. Yikes. And negative 3 is somewhere in there. I'm not going to try to get super awesome with that, but it's going to come like this. Oh my goodness. No, it's not ready. It's going to come in like this, and it's going to go something like that, right? And so it's an upside down exponential decay. You know, like just a generic exponential decay goes like that. Right, but this one got reflected over the x, so it's an upside down one. So it's decay, but it's going towards 0 as the x gets bigger and bigger and bigger. So if I put a 2 in there for x, I square 1/2, I get 1/4 times 1/4 times negative 6 is going to be negative 6/4, which is negative 1.5. And you know, I could just start doing this a little different way, right? Instead of putting the number in and evaluating it, I could follow the pattern of multiply by 1/2. So if I take negative 6 and I take half of that, I get negative 3. If I take half of negative 3, I get negative 1.5. If I work backwards, I'm going to be multiplying. So negative 6 times negative 2 is going to be negative 12. This one should be negative 24. This one should be negative 48. This one should be negative 96. And so you can see like negative 96 ends up being way down here, and you'll see how that graph follows along. Follow-up question with the domain and range. What is the domain and range of this graph? Well, are there any values for the domain or x values that I cannot put in for x? And in this case, there are no restrictions, so x is all real numbers. So all reals. You can put anything in for x. The range, however, the y values, are going to be restricted in this case to all less than 0. Because we have an asymptote at this horizontal line, y equals 0, your graph is never ever going to touch that line or cross that line, so all the y values then have to be less than 0. Okay, moving on to number 5. Sketch a graph of the following exponentials. Be sure to label y-intercept on the graph. So this is where we want to find if it is decay or growth, and then find your starting point and sketch a little graph. Doesn't have to be perfect, just a sketch. So my starting point here when x is 0 is going to be 8. So I start up here at 8, wherever that is, just make a little sketch. You can make a little label. That's going to be 0, 8. And this is going to be exponential growth because that is a number bigger than 1. So because it's growth, it's going to come through and it's going to get bigger. Just make a little sketch like that. So if that confuses you, you could plug a point in to the right of 0 for x, and you would see that you'd get 1.5, and 1.5 times 8 is going to be 12. So then your next point, if you put a 1 in, you'd get a 12 out. So you'd be up here at 112. So you could plot points too if you're confused and needed another way to figure out how that graph goes. Over here we have a negative starting point, so we have to be a little careful with that. So my starting point when I put 0 in is -2, so I'm going to be down here. And it's going to be a decay. So this one is actually going to get smaller and smaller and smaller. Now this is a little bit of a weird scenario, so I like to think of it as a reflection. So a normal exponential decay looks like that. So then if I flip that and I have a negative exponential decay, it's going to go like that. Because anytime you have a negative out in front, it flips it over the x-axis. All right, moving on. Number 7, identify if it's linear or exponential, and then write an equation. So we talked about if it's linear, it's going to be adding to get the next numbers for y, and you could think of it as adding a negative if it's going down, and if it is exponential, it will be multiplying by some number. And if it's like dividing, then you can think of it as multiplying by a fraction, which means it would be decay because multiplying by a fraction means it's getting smaller. So as x increases by 5 each time, y is going to be decreasing by 2 each time, it looks like. So this is going to go down 2, in a subtraction, or adding -2, right? So that is going to be a linear. And if this is going up by 5 each time, and I was talking with Dave about this one, nice job, Dave. If this is going up by 5 each time and y is going down 2 for every 5 it goes over, isn't that just the slope? Yeah, it is. If you go up 5 for every, or I'm sorry, down 2 for every 5 you go over, what's the slope then? Down 2, right 5, down 2, right 5. That's -2 over 5. So -2/5 x, and then look at right here. We have the y-intercept, they give it to us as 12, so I can just put in a little plus 12 right there. Number 8, this one's kind of nice because it just goes up 1, up 1, up 1 on the x, so that's slick, and then it seems to be multiplying by a 2 each time. So this is a times 2, times 2, times 2. So the growth factor is times 2, but it looks like we have a negative starting point. So that's exponential. It's going to have a starting point of -4, and you know that because that's where the x is 0 part. That's a starting point, the y value when x is 0. And then my growth factor is going to be 2 to the x. You could check that by putting in a few values and see if you get the right result. So if I check it and I put, let's say, 2 in there, put a 2 in there for x, 2 squared is 4, 4 times negative 4 is negative 16. Good, I feel good about it, I checked my work. This next one's a little bit of a tricky one. This one's going up by 2 on the x, so it goes up by 2, up by 2, up by 2, and on the y, it's dividing by 3 or timesing by a third. Okay, so it appears to kind of have a 1/3 decay rate. However, it's going up by 2 each time, so it's really not timesing by a third each time because it's going down by 2, so we got to be a little bit careful on this one. So let's start building our equation and see what we can do. We have the starting point we know is going to be at 3. So this is y equals 3 times, I'm going to use b for the base, b to the x. Now we have a whole bunch of solutions in this table, so we can take any one of these solutions and substitute them in for y and x and solve for b. So I'm going to pick 2, 1. Some people pick 0, 3, but that was kind of a bust because we'd have 3 to the, sorry, not 3 to the 0, it's b to the 0. So, oops. Then people would have b to the 0 equals 3. But then it's like, wait a minute, anything to the 0 is, and then that just ended up being not very helpful. So I'm going to pick the next easiest point, which was 2, 1. So put 2 in for x and 1 in for y. And I'll have 1 equals 3 times 2 to the x. Okay, now I need to solve that for x. So I'm going to divide both sides by 3, and I'm going to switch this over because I like the variable on the left. So 2 to the x equals 1/3. I got that by dividing both sides by 3, right? So now how do I, wait a minute, I'm totally screwing up here. I've screwed this problem up like 3 times today. Duh! Silly me. I didn't plug in for x. I plugged in for b for some reason. Okay, so y is going to be 1 equals 3 times, I'm trying to find b, so I should have plugged in x is 2. Okay. Now divide by 3, I still get the same thing, but now instead I have b squared equals 1/3. All right, how do I get rid of a squared? You are probably thinking square root. Yep, square root or to the 1/2 power. And so I'm going to take 1/3 to the 1/2 power, which is a square root. So the square root of 1/3 is going to be the square root of 1 over the square root of 3. And after I rationalize that and I get rid of the radical in the denominator, because that's just not very proper, I'm going to get root 3 over 3. And so this equation ends up being kind of a crusty one. It's going to be y equals 3 times root 3 over 3 to the x. All right, that's a little above and beyond. That one is kind of a high-flying question. All right, then we get into the back side. We have some compound interest stuff, and I told you we'll give you the formulas. So we're going to invest $5,300 at 5.7 compounded semi-annually. Semi-annually is twice per year. That one's a little weird. I had a student ask me that today, and then I asked them, and they did, and they actually Googled it, and it was twice a year. So nice job on them for Googling it and being their own problem solver. So we're investing $5,300. So the amount after we compound interest is going to be equal to the $5,300, the P we invested at a rate of 1 plus 5.7, so that's 0.057 over semi-annually is going to be 2 times a year. For 16 years, that's going to be 2 times 16, so it's going to compound 32 times. Okay, and then I put that in my calculator, and I come up with $13,026.07. Okay. Next question, we're investing compounded continuously, $6,200 at 4.6% for 8 years. So compounded continuously is where we have our PE to the RT. So we're doing $6,200 is our principal, and continuous is using the math constant E, and that is to the 8 times 0.046 power. So now we have to just calculate this. We get 8,958 and 2 cents. Money. All right, cruising along here. Number 12. What is the rate of decay if a population goes from 3,582 to 2,799 in 7 years? Okay. Well, it's getting smaller, decay, so I'm going to start with the smaller number, 2,799. And that is going to equal the original amount, 3,582, times the decay factor. I'm just going to leave that as an x right now, and to the 7th power. So I need to solve for a missing base x. So I'm going to get the 300 or 3,000 to the other side, and then I'm going to take it to the 1/7 power. So clean this up a little bit. Whoops. Switch colors. Say we have now x to the 7th is equal to the ratio 2799 over 3582. And to get rid of the 7th power, I take both sides to the inverse to that, which is to the 1/7 power. And I will have my, sort of have my rate of decay. There's a little twist at the end here. So take 2799 divided by 3582 to the power of 1/7. It's going to give me 0.965. Okay, so my x is 0.965 if I round it to the nearest thousandth. And so that is not really my decay rate. That's going to be how much I have left in each subsequent year after it decays. So really that's saying I have 96.5% of what I originally started with after, each year is decayed. And then the next year I have 96.5% of that decayed stuff. And pretty soon it starts to decay and decay and decay. So really my decay rate, or my rate of decay, is going to be 1 minus that. So if I chop it off at 0.965, I could say my decay rate would be 3.5%. Okay. Keep on keeping on here. At what rate would $2,350 grow to $4,720 if it's compounded continuously for 6 years? So we're growing to 4,720 from 2,350, and it's continuous, so it's going to be e to the 6r. Okay, we're going to have to solve where a variable is in the exponent, so this is going to require a log. Divide both sides by the 2350. And now what that's going to do is that's going to get my e to the 6r all by itself, equal to the ratio 4720 over 2350. Now, how do I get that exponent down from, that variable down from the exponent up there? That's where I use a log. If it's e to the power, I'm going to use a natural log of the stuff, which is 4720 over 2350. And that's going to equal 6r. So now to solve for r, I just need to divide both sides by 6. So I take all that stuff and I divide it by 6. So r is equal to the natural log of that goofy ratio that I had, 4720 over 2350. And you don't need to type base e in or anything because the natural log implies base e, and that's all divided by 6. So I'll evaluate that on my calculator here. You could do this in one step or two. So I find my natural log, it's underneath the e to the x button. 4720 divided by 2350. I got 0.116. So 0.116. That means I need an 11.6% rate for that to happen. So rate 11.6%. Okay, cruising along, last page. How long will it take $4,600 to grow to $8,600 whatever dollars compounded quarterly? So same type of question, but now we're doing compounded quarterly. So this is going to be 8,675 equals principal of 4,600 invested at 1 plus 0.037% over quarterly is 4, and then that's going to be then to the 4t. Okay, so we have kind of some ugly numbers in here, and I've been encouraging you to not round them off so that you have an inaccurate answer. So this is going to be kind of a messy expression, but I think you can handle it. So we want to divide both sides by 4,600. So we do that, and we're going to get 1 plus 0.037 over 4 to the 4t power equals the ratio after I divide by 4,600 of 8675 over 4,600. Okay, so I divided both sides by 4,600, that's what I get. Now I'm going to rewrite it as a log, change colors here. So this is going to be sort of an ugly log. This is going to be the log of this ratio, 8675 over 4,600. And the base is going to be that 1 plus stuff. So the base, I'll write that in red, is going to be that 1 plus 0.037 over 4. So that's kind of crusty, and that equals 4t. But I don't really want to know what 4t equals. I want to know what t equals. So once I take all of this stuff, this ugly log with that crazy base, I want to take that and I'm going to divide that, because I divide both sides by 4. I'm going to divide all that stuff by 4. And then I'll get my t value. So I ended up getting a t value of, 17.2 years. Okay. Number 15, population of a school is 800 students, increasing at a rate of 2% per year. Find the population after 6 years. All right, so I don't know my amount. After increase, I know the original amount was 800 students. We're increasing at a rate of 2%, so that's going to be 1.02. I know it's a little weird going back from like doing a money problem to doing just a regular exponential growth problem. So this is good that I think we threw this one in here. So now we have 800 times 1.02 to the, how many years? 6 years. Okay, so calculate that. And we will get, let's see here, 800. $900.9 students. So I will say this is approximately, I'll just round down because you can't have 92% of a person. So 900 students. That will be after 6 years of growth at 2%. How long will it take to get 1,000 students? Okay, well now we're solving for a different variable. We're solving for the t. So now we say, all right, I want 1,000 students. I started with 800. What is the, the rate is still 1.02. And how long is that going to take? So now again, we're looking for a value of an exponent variable, a variable and an exponent. So that's where you use a log. So now we take this and we rewrite it as a log. The log of, well, I guess I'm getting kind of ahead of myself here, but I divide both sides by 800. So then I'm going to get 1,800ths or 10/8 or 5/4 or 1.25. Sometimes it's nice and neat and perfect like that, and you could reduce it. But you know, I just write it in there. I'm using my calculator anyway, so I'm just going to write in the log of 1,800ths, and I know the base is 1.02. So I got my base of 1.02, and that's going to equal my t. Equals t. So 1.02 to the t power equals 1,800ths. Go ahead and solve that, and you'll find out how many years it's going to take. So log 1.02 base. I really like these inspires because it just pops the base right in there for you. And then we have 1,000 divided by 800, and we end up with 11.26 or 11.3 years. 11.3 years until that happens. Okay. Last question. Francium or francium, I don't know how you say that. 233 has a half-life of approximately 22 minutes. Find the amount of francium 233 left from an 80-gram sample after 88 minutes. All right, so we have an 80-gram sample. That's going to be our initial amount, 80 grams. And it's going to be a half-life, so I'm going to do 0.5 as the base. That's the decay. And then the tricky part here is it halves every 22 minutes. And I want to know after 88 minutes, so I got to make sure that I do the 88 minutes divided by the half-life of 22. So really, it's only going to be halving 4 times. It halves every 22 minutes. Well, if you want to know after 88 minutes how much is left, well, it had halved 4 times in between there. So now we run this on our calculator, and we get 5. 5. Hi, Aaron. 5. What is the answer? What does that represent now? Aaron's here. 5 grams. Yeah, grams. We have 5 grams left. Okay. There we go. Under 30 minutes. So happy studying.